All right, so it is once again a Friday afternoon, and I just find it it's impressive that it was 2 weeks ago that I did the first the nuclear beer video for the YouTube, and only found it appropriate that we would cover the opposite end of the nuclear energy spectrum, because this is something that has kind of been getting a decent amount of news coverage in the past few years, and it's something that has been part of science fiction for a long time. Nuclear fusion. So nuclear fusion, what we do in the nuclear power plants that are operating all over the world, all of whatever number of them, they use fission. So fission and fusion. Fission is when we take things and we break them apart. We take a big thing and make it into smaller pieces. Fusion is when we take lighter things and we merge them together and make one big thing. So it's only appropriate. The last video of this, the nuclear energy thing, was I was consuming a craft brew that was quite heavy on the brew side. It had a nice cloudy, very high level of flavorings in it, and fairly high alcohol concentration. Today we're going with this clear American Pilsner. Something that a lot of people in the old world would probably consider to be equivalent to seltzer water or urine or something like that, but we're drinking it because this is light, and we're all about light elements when we have nuclear fusion. So let's begin here. Take a sip. In the meantime, I brought the white marker board upstairs because it had little of no value downstairs. It was a pain in the ass to write on. So temporarily we just stuck it on the doors here, and hopefully I can write on it without it falling on the floor and causing a disaster. So nuclear fusion. So most people are probably, at least somewhat aware, hopefully, that nuclear fusion is how the stars, like the sun, are obtaining their energy. So we're using hydrogen, which is the most abundant element in the universe, and we are taking that hydrogen and we're merging them together, and we're converting it to helium. And in the process of doing this, there's a very large amount of energy that's released from this reaction. Actually, not this particular reaction, but from two hydrogen atoms coming together. So it's the same kind of concept as uranium. So uranium, you got this big uranium nucleus, 235 protons plus neutrons in a uranium nucleus. And the whole idea with fission is it's actually pretty easy to get fission to work. So you have this big ass uranium nucleus over here, and you shoot a neutron at it at a fairly high speed, but not too fast. And there's a probability that neutron is going to go into that uranium nucleus, and it's just going to spontaneously make that uranium nucleus just break apart into pieces. So you might get a barium atom and some kind of somewhat heavy but not that heavy nucleus that comes out of the uranium. And then in the process you also get energy. So something like 200 mega electron volts of energy or something like that. The units don't matter, but that's the heat that heats the energy that heats the water up in the nuclear reactor to generate electricity. And a lot of people, I think, might see fusion as being somewhat similar, but there are a lot of differences. A lot of differences. And there's a lot of reasons why in that list of differences that we use fission and not fusion. Because on the surface, you might think, well, hydrogen, you know, how many hydrogen atoms are in this beer? There's a lot. This is like a half a liter of beer that's here, and you know, half a liter is 400, 500 grams. A mole of water is 18 grams, and there's 10 to the 23rd molecules of water in a mole, and there's 2 hydrogens on each one. That's a lot of hydrogen atoms that are in here. A lot. And if you did the E equals mc squared on this, this would destroy, if this could be, energy would be released all at one time, all that nuclear energy, it would demolish everything within miles around here. It's incredible to think that that's the case. But the fact of the matter is, even though that energy is there, theoretically, it's very, 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 very difficult to get it to come out. Getting the genie out of the bottle is why fusion is it's so difficult. So I kind of want to spend more time on talking about getting the genie out of the bottle than the actual fusion, but we have to kind of go over fusion and how it works. Okay, so fusion can happen in a lot of different ways. There's there might be like a half a dozen or more different varieties of fusion out there. Like what happens in the sun is what they call the proton-proton chain reaction. So basically you're just taking single protons, hydrogen 1, the hydrogen 1 nuclei, so the one isotope of hydrogen, single proton in that nucleus. Okay? And you're just putting those together and you're building up and you're making helium out of them. But we also have other isotopes of hydrogen. Okay? And they are less abundant. But for us feeble little human beings, it's much easier for us to do fusion with these hydrogens than it is for this one. And there are hydrogen, deuterium, and tritium. Tritium, that's a real thing, yes. And tritium is the thing that's in the hydrogen bomb that makes this is the reactions that happen using tritium. That's the key fuel for nuclear weapons, thermonuclear weapons. This is an important element. This is extremely, extremely rare, very, very rare. This is radioactive. Okay. This one, the deuterium, isn't really that rare. So out of every hydrogen atom in this beer, or in any water solution, liquid, water-based liquid, about 1 in every 6,000 hydrogens is a deuterium. So there's deuterium in here right now, and in my body, and in the cat over there, and in this everything. Deuterium is there. Okay? And then, of course, this is regular old, plain old, boring old hydrogen. And for us to make that as reactions happen with this one is very, very, very hard. Whereas these two, it's easier. And I'll explain why, sort of, at least from what I know offhand. I'm not necessarily expert. I'm not a nuclear physicist, but I'm just going to go over the energy aspect of it. So, to get the fusion to actually happen, you need some pretty extreme conditions. So, the problem is, so like I said, fission, uranium, heavy, heavy, dense element. Neutron will go into that nucleus and spontaneously that uranium will just blow up and it will give you energy. Quite easily. All I need is a specific mass of uranium, a sphere that's a particular size, and it will spontaneously fission. And if that happened, it would be very bad for anybody standing nearby. Look up the demon core online and you'll learn about, even though that was plutonium, but it was the same idea. Demon core. So that was fission. Fusion is different because we got our, say we got those two isotopes of hydrogen, deuterium and tritium. So I'm going to do my deuterium. So I got my proton and a neutron. Okay. We got our tritium. We got our proton. We got two neutrons on the tritium. So with fusion, we want to get these to come together. We want them to merge into one. And that one would be an isotope of helium, helium-4. So you got two protons and two neutrons. And then we have an extra neutron left over. And that extra neutron is very important. So we want to merge them. But what's the problem here? The problem is, you take two magnets, a north and a south pole. You take the north pole of one magnet and the north pole of the other, and you try to put them together, and they will not stick together. That they repel each other. The same thing happens here. These atomic nuclei are all positively charged. The proton is positively charged. We're not worried about the electrons. They're not here right now. They're way up here and up in the attic and up in the wherever, up in space a little ways. We're worried about the nucleus. Positive charges repel one another. So we got positive, positive, and they don't want to stick together. They just do not want to come together. All right? They don't want to do it. But like a lot of things in this world, if you apply enough energy, eventually it'll happen. So it's what they call the Coulomb barrier. I don't know the physics of it exactly, but I just know that's an energy barrier. You need to give these nuclei enough energy to overcome this electrostatic force, and they will come together and they will merge into a helium. So how much energy is that for this reaction, this deuterium-tritium? And how do we apply that energy? I suppose there's a lot. I suppose that I don't know if it matters how you apply it, but the way that it's being done and the way it's in theoretical in practical physics is through heating it up. And over in France right now, there's a massive, gigantic thing being constructed called ITER. ITER. Used to stand for International Thermonuclear Experimental Reactor. They figured that was too long and the public isn't really comfortable with the word thermonuclear, so we're just going to call it ITER. 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 Okay? And ITER is what they call a tokamak. So it's a vessel that's designed to heat these nuclei up to the temperature that you need to break the Coulomb barrier. All right? And this vessel is enormous, and this entire facility is probably one of the most complicated things that human beings will have ever built. Even more so than the Large Hadron Collider. Even more so than pretty much every physics experiment to date. It is absolutely enormous. All right? And the deuterium-tritium fusion requires a temperature, and it's dependent on pressure too. But it requires a temperature. I think it's around I don't know. It's a nice cool temperature of like I forget. 100 million Kelvin. I mean that's not that hot, right? I think my kitchen stove gets hotter than that, right? 100 million Kelvin. What's that in Fahrenheit? It doesn't really matter. I mean, at this level, you can round off to the nearest million, and nobody would really notice. But 180 million degrees Fahrenheit. So that's how hot we have to get those deuteriums and tritiums in order to get them to turn into helium and give us that vital juice that we need. So that's really, 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 really hot. And like, what substance do you know of that can withstand that temperature? Tungsten, iridium, molybdenum. I think the melting point of tungsten is like, forget what it is. It's I don't know. What is it, like 6,500 Fahrenheit or 6,500 Celsius? So that's a lot. It's a lot lower than our 180 million degrees or 100 million degrees. So the Tokamak, which is that reactor that they're building over in France, the ITER, is designed to contain the fusion in a plasma with a magnetic field. So because there's no such thing as a material that you can just put that, just throw it in this bottle and heat it up to 100 million degrees. It doesn't exist. So now I'm kind of wandering into the side of the physics of actually application of using the fusion to generate energy. And the problems with fusion are just, there's so many issues with it that have to be overcome before it becomes anything that anybody ever uses. So, okay, let's see. You need to heat it to 100 million degrees and all that stuff. So it sounds impossible, right? But the heating isn't really the hard part. Because I could actually build a device that I could sit right here on the bench top that would do nuclear fusion. They call it, one of them is called a fusor. Fusor with an O, fusor. There's also one called a polywell. I don't really know the details of these, but they use electrostatic forces to accelerate the deuterium into a high enough speed that you get the energy to make the nuclei come together. And you can actually get nuclear fusion to happen on the bench top. And you can detect that through the neutrons that are emitted from the reaction. All right? But the problem is the amount of energy that you have to put into the fusor in order to make the reaction happen is far in excess of what's actually coming off the fusion. So you might have a few fusions per second happening in your benchtop fusor, but you're putting in 1,000 watts of power or whatever number of power to make your plasma and to accelerate create the acceleration voltage for the ions in the plasma. So your fusor can make fusion happen, but it can't make it happen fast enough to create enough energy to make it a viable energy source that not only powers the fusor, but also generates electricity that you can sell. So then they tried building fusion devices like, I think there was a Joint European Torus. There was a device I think it's out in California called the National Ignition Facility, where they tried using lasers to heat up a capsule of fuel, Deuterium and Tritium fuel, to a high enough temperature using a laser pulse. Then there was a bunch of Tokamaks that have been built throughout the world, and none of them have yet come anywhere close to creating as much or more energy coming out of the fusion reactions as what's being put into it in the form of electricity and other energy to drive the device. Okay, so now we got ITER. So ITER's being built. It's costing tens of billions of dollars. There's like 7 countries or groups of countries that are contributing the funds to build this ITER. And the whole idea here is surface area to volume ratio. So they're building the machine big enough that the energy losses, which is through your outer skin of the machine, through the outer surface area are less than, or actually kind of equal to, what's being created in the volume of the machine, which is the plasma. So Tokamak is a donut-shaped device. Okay, we're just going to try to draw a cheesy donut here on the white marker board. And we're looking at the donut from above. So this is the center of the donut. And this center of this donut is a magnet solenoid coil. So there's magnets that are all around here. Okay, this whole thing has magnetic coils that surround it. And they're superconducting magnets. So they carry electricity and they're electromagnets, and they need to be cooled to basically liquid nitrogen temperatures. Or liquid helium, I believe, maybe even. And there's an entire cooling system in the ITER project that is designed to keep this magnets cool. So you've got this like magnets like 4 Kelvin, you know, 4 degrees above absolute zero to make these superconducting magnets work. And then in the middle of here, you've got this plasma that spins around at 100 million degrees. See, that's a huge temperature difference. And there's like plates on the inside of here that shield the radiation that comes off of the reaction. Okay? Shield the people and the equipment that surrounds the reactor. Alright, now I'm not probably drawing this to accurate depiction, but I'm just envisioning what it might look like. So your plasma is inside here, and the magnets create a magnetic field. Because plasma is electrically charged, the magnets can actually act on it and they can confine it. So the magnetic field keeps the plasma away from the walls of the tokamak. Alright? Because you don't want this hot plasma hitting the walls. It will erode the material, so it'll sputter off the metal, and it will eventually destroy the tokamak if the plasma touches the walls, even if they're made out of like tungsten or silicon carbide or something crazy like that. So, got your plasma. Alright, our magnets are running. We got a radio frequency generator that basically heats this plasma up. This plasma consists of like argon gas and hydrogen, and it's probably just regular hydrogen that dilutes the fuel. You know, your deuterium and tritium. They might use inert gases. I don't know what gases they use other than D and T. Deuterium and tritium. Fuel. Alright? So, now how do you get the energy out of the tokamak? I always wondered this, and before I looked it up online. How do you get the energy out of the tokamak? What do you put a steam coil in here, like that, and the plasma goes through the steam coil? That's what we do at a coal-fired power plant. We put a coil of pipe inside of a furnace, and the fire goes past it, and it turns the water into steam, and it goes to a turbine and make electricity, right? How do you do it here? And this is it's very interesting, it's very innovative, but yet it's also problematic at the same time. So remember at the beginning, and I'm just going to erase this plasma, and I'm going to write the reaction in here. So I'm just going to call it D plus T gives us helium-4 and a neutron. So we have a neutron in deuterium, 2 neutrons in tritium, but there's only 2 neutrons in helium-4. So we have an extra neutron just kind of there, just hanging around. Oh yeah, hey guys, and extra neutron. Where does it go? What happens to it? It's kind of like fission reactors. The neutron goes and it zings away from the reaction, and just about all the energy. There's energy in the heliums too, but the neutron carries energy because it's got mass and it's got kinetic energy, and that neutron goes zoop, and it flies through space, and that neutron, shouldn't have erased it, the neutron, most importantly, is neutral. So it's not affected by the magnetic field created by these superconducting magnets. So the neutron can just go wherever. It just flies, in a line of sight wherever, and it hits the walls of the reactor. So this tokamak, somewhere between the walls of the reactor and the outside, there is going to be, and I say going to be because ITER is not going to have this feature. Okay, because ITER is not going to generate any electricity. The only thing that it's going to do is prove if it's physically possible with this machine to create more heat from the energy, actually I should say energy, not just heat, from the plasma than electricity or energy that's put into the plasma. And I believe that that electricity does not include what's needed to run the superconducting magnets. It does not include the facilities of the plant. It just includes how much radio frequency microwave power they have to put into the plasma to get it hot enough to make fusion happen. And versus what fusion's actually producing. So they want a 1-to-1 ratio. And sorry to say, but to generate power, we need a better than a 1-to-1 ratio. We need like a 4-to-1 ratio. Okay? A 3 or a 4-to-1 ratio. So the fusion needs to produce about 4 times more thermal energy than what's needed to run the entire fusion nuclear power plant. And ITER is not going to reach that level. It's just going to prove the possibility of a 1-to-1 ratio. Because so far we've only achieved fractional ratios. So come on. So the cat's getting upset. So the whole idea here is that you got to get the energy out of the plasma. And after ITER, so let's say they achieve the 1-to-1 ratio, and they decide, okay, now we're going to build another nuclear fusion power reactor, and we're actually going to put in the facilities to capture the energy from the plasma. So surrounding the vessel. Now this vessel, like I said, it's under vacuum, high vacuum, and it runs at less than atmospheric pressure. It's got superconducting magnets, and there's a very, 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 very hot 100 million degree plasma that circulates inside. Neutrons zing out from the reaction, and they strike the walls of the reactor, and you've got something embedded in the walls of this reactor that can convert that neutron's kinetic energy into heat, thermal energy that we can use. So theoretically, the way that this is proposed, this is going to happen, is they plan to use lithium. Lithium, that's a hot commodity right now because that's what the batteries use. The batteries are using it much differently than what we're going to use it here. But lithium, so you got your elements, periodic table of elements, you got hydrogen, helium, then lithium. And the cool thing about lithium is we can take a neutron and we can fire it into the lithium and it'll give us tritium. Okay? So like I said before, tritium is very rare. There's not a whole lot of tritium in the world at the it's not something that you can just go out to the river and pick up a cup of water and there's tritium in it. It's not that way. So we have to make the tritium. And the proposed method of making that is by hitting lithium with neutrons. So when you hit lithium with neutrons, you get your tritium plus the lithium gets hot because this has kinetic energy. There may be some heat released by the transmutation of lithium to tritium. I don't know. All I know is that this is an exothermic reaction, either because of just pure kinetic energy loss or something else in addition to that. So you get your fuel and you get your heat. So your neutrons carry the energy out of the fusion reactor, and they heat up the lithium blanket that surrounds it, and you put your water coils or whatever heat exchange fluid you're using through the lithium blanket, and that's how you get your energy to make your steam to drive your turbine. And at the end of the day, nuclear fusion, all it's going to do is make steam to drive a turbine, the same way we've been generating electricity since the Pearl Street Station, Thomas Edison days. So that's basically how it's proposed to work. When will this happen? I'm probably not going to be around to see it. I doubt that anybody who's alive today, except for maybe somebody that was born, this year or in the past year or two, would probably never see this. I mean, this is something that is so far off. There's a lot of challenges with fusion, a massive, massive challenges, and every time I see an article online that talks about how this is going to save humanity from global warming and all this stuff, it's not going to happen. I mean, so when is ITER going to start up? When are we going to prove if it's possible to get a 1-to-1 ratio of heat coming out of the reaction versus electricity going into the plasma? And this has been struggling with timelines. So they believe that they plan to do testing with hydrogen. I'm talking regular hydrogen, beginning in like 2025. So 4 years from now, we're going to fire up the plasma in the ITER using regular old hydrogen just to do testing. It's not going to yield any neutrons, and that's critically important, because once they fire up a DT plasma in the Tokamak, those neutrons are going to irradiate that entire machine, and they're going to start to make the metal radioactive, and the metal or whatever it's built from. They're going to cause activation of the construction materials of the equipment. And now all of a sudden, people can't go into it. And this is where I run into a lot of misconceptions about fusion versus fission, because everybody's well aware of the nuclear radioactive waste hazard of fission power plants. Okay, it's really a very clear idea. You use the fuel, and after you're done using the fuel, you've got this fuel element that is extremely radioactive. And it's effectively a waste product. It's very difficult to manage that because of the radioactivity aspect of it. But fusion is not free from that problem. If you're like, oh, it's just hydrogen, it's clean, it's safe, there's no issues. But there is the issue of the power plant itself, the equipment that's being used becomes irradiated with neutrons, and it becomes radioactive. You get radioactive activation products that happen inside that tokamak. And it makes it very challenging to do maintenance. And a lot of the reasons that ITER has had such delays is because they're trying to figure out ways to do remote handling of all of the maintenance activities of the reactor. So you got to be able to do maintenance with an neutron-activated tokamak. So 2025, you're going to do hydrogen, and then they're going to try to fire up a deuterium tritium plasma in 2020 or 2036 or 2035, 10 years after the hydrogen. So we have to wait until 2035 before they even try to do actual fusion that yields a net, any kind of energy output. And then there's got to be all sorts of testing done to try to get this to our 1-to-1 ratio. 1-to-1 ratio of plasma power in and fusion power out. Plasma power in the form of electricity, plasma power out in the form of effectively heat, or neutrons, or whatever is calculated to be emitted from the fusion reactions. And that's nowhere near what we need to drive a good steam power plant or, you know, a good one would be 3 to 1. Good steam power plant, you need 3 units of heat for every unit of electricity that you're making. So ITER is basically going to be a net consumer of electricity. They've got a 400 kilovolt substation at the ITER site that's drawing power from the French power grid that's going to use like 500 megawatts of electricity or something. This thing is going to consume, you know, gonzo massive levels of power to light off that plasma. This is huge. It's a massive thing. And at the end of the day, all it's doing is just trying to prove a 1-to-1 ratio of, like I said, electrical power input to the plasma and fusion power output. And then there's a proposal to build another nuclear fusion plant called Demonstration, clever name, huh? Demonstration power plant that would basically take the Tokamak to the next level of putting in the lithium absorber blanket and capturing the neutrons and producing both tritium and thermal energy that could then be diverted off to generate steam to make power and drive a steam turbine. I think most of the projections I've seen for this are in like the 2050s and 2060s. So it's possible that if everything goes perfect and that all the timelines are good, that somebody who's very young right now may see the day where we have a working fusion power plant. But I don't think I'll be seeing it. The other thing with this is the whole concept of you know, unlimited energy. The cost of these facilities right now is so high that you could never even you know, even begin to calculate what if that would be even possible. We have a much better probability of using solar panels and wind turbines than we do of using nuclear fusion at this point in time for, you know, having carbon-free, CO2 emission-free energy that doesn't contribute to global warming, climate change type situations. That's really about as far as I should probably go, because it's getting a little long. Nuclear fusion, really good sci-fi concept. You yield massive amounts of energy from a relatively abundant and you know, easy to handle fuel, but super hard to get it to happen. Like, it's just fission. Nuclear fission is so much easier that, and like I said, solar panels, wind turbines, and nuclear fission. Nuclear fission obviously works very well, and it's quite practical. So these lights in this room right now, and this camera, is being powered more than likely by nuclear fission because it's dark outside and I'm not getting sunlight here. So we're using fission at the moment, not fusion. If you want to use fusion, if you really like fusion, the best fusion reactor to use is the one that's already operating. It's about 93 million miles from here. And comes up every day, goes down every day. You get to see it. So that's really all I've got. My Pilsner, light Pilsner, my light elements are getting close to the bottom. So that's it.